Yeah, thank you for the introduction. I'm Siyuan from the Chinese University of Hong Kong, and this is our recent study. So in this study, we aim to improve the write performance of key-value stores. Well, based on recent studies, write-intensive workloads have become dominant in production key-value stores. So such as Twitter's Cache clusters or Facebook's RocksDB production. What is challenging to achieve high write performance? First, given a write request, it will suffer from large round-trip latencies, including like transmission latency between switch and server, and the extra queuing delay if the server is overloaded, and the server-side processing latency. And what's more, for distributed key-value stores, the Skewed workloads will incur server-side imbalanced load. That is, a small number of servers may be the bottleneck and hence undermine the write performance further. So to improve the write performance, programmable switches provide an opportunity. So first, this is the architecture of a programmable switch. It includes two parts, control plane and a data plane. Well, the control plane, that is the switch OS, can config or control the switch data plane. Well, in the switch data plane, it includes multiple pipelines, and for each pipeline, it includes a series of stages to process traversed requests or responses within switch memory. So we can deploy a write-back policy into the switch. That is, we can cache the hot records into the in-switch memory to absorb the write on the cache records instead updating the servers immediately. So it can improve the write performance by an in-switch write-back cache. However, in-switch write-back caching exists the following challenges. Well, the first challenge is a performance challenge. Switch data plane has very restricted programming language, programming model, and limited resources. So we have to offload cache management to the control plane, the cache management including cache admission and cache eviction. Well, however, controller is much slower than switch data plane. So it may incur large controller to switch latency and degrade the I/O performance in the switch data plane. Well, the second challenge is availability. Well, under the write-back policy, the latest records could be stored either in the switch or the server. So we have to synchronize the switch and the server to ensure that the latest records are always available to the clients. However, if we simply resolve the controller to synchronize the switch and servers, it will incur large synchronization overhead due to slow control plane processing. And the third one is a reliability challenge. Under the write-back policy, the cache records in the switch can be the latest versions, yet not updated to the servers yet. So after switch failures, all such in-switch latest records could be lost and undermine the reliability. So there's the challenges about in-switch write-back caching. Well, to fix the challenges, we propose FarReach, a first available and reliable in-switch write-back cache. We mainly propose three design features, including non-blocking cache admission, available cache eviction, and crash consistent snapshot generation with zero loss recovery for the three challenges respectively. Well, I will detail them in the following slides. Well, we implement our prototype based on a Tofino switch, and we implement the in-switch cache by P4 and the server-side key-value stores by RocksDB. Well, we conduct extensive experiments based on Tofino-based evaluation. For example, FarReach can achieve up to 6.6 times throughput gain compared with the baselines on the 128 simulated servers. So we also have open sourced our prototype. But before going to the details of our design, let me first introduce the overview of our architecture. Well, as you can see, we deploy an in-switch write-back cache into the programmable switch. We cache the hot records into the switch such that the writes on the cache records, that is the writes with cache hits, will be absorbed by the switch instead of accessing the backend server to improve the write performance. We also, due to the switch limitations, we also offload cache management to the controller. So controller will use the interfaces provided by switch OS to manage the in-switch cache, including admission and eviction. Well, in the following slides, I will show how we carefully co-design the control plane and the data plane to fix the challenges mentioned before. Well, first let me consider the performance challenge. Here's a problem of performance in cache admission. So suppose a request, say a write request issued by a client, arrive as a switch and trigger cache admission to controller. So as controller is much slower than switch data plane, before controller admits the record into the switch, the subsequent write could arrive as a switch. So if we block the subsequent write in the switch, then it will surely decrease the I/O performance in the switch data plane. But if we directly absorb the subsequent write in the switch under the write-back policy without blocking, then it will decrease the availability. The reason is that for controller lies in the control plane, so it has no view about the subsequent writes traversed in the data plane. So controller will overwrite the latest version carried by the subsequent writes by a stale version reported by server before for cache admission. So if we directly process the subsequent writes in the switch without blocking, it will undermine the availability. Well, to fix the problem, we propose non-blocking cache admission. The idea is that we can process the subsequent writes in the server side. So the server will have the latest version. Well, so as the latest version is located in the server now, so controller will mark the in-switch record as outdated. Well, for subsequent, after the record is admitted into the switch, for the subsequent reads on the outdated record, as the latest version is in the server side, so FarReach will conservatively forward the reads to the server side to get the latest version for availability. While for, as a conservative reads will introduce extra read latencies. So we will try to limit the number of conservative reads. So our idea is that we will mark the in-switch record, the outdated record, as latest as early as possible. We observe that the switch can monitor all traversed requests and responses. So for each write request with the latest version issued by the client, and for each read response with the latest version provided by the server, we will mark the in-switch outdated record as latest. So after that, as long as the in-switch record has been marked as latest, all reads and responses will be directly processed by the in-switch cache under the write-back policy without accessing the server. So under the write-back policy, it can improve the write performance. And that's how we fix the performance challenge by non-blocking cache admission. But second, we consider the availability challenge. Here's a problem of availability in cache eviction. Under the write-back policy, the evicted record could be the latest one yet not updated to the servers yet. So controller has to load the evicted record from the in-switch cache to the server for persistent storage. But as we mentioned before, the controller is much slower than switch data plane. So during the process of cache eviction, subsequent writes could arrive as a switch. If we directly process the subsequent writes without synchronization between switch and server, then it will be difficult for FarReach to distinguish which one is the latest version, either the in-switch record or the server-side record. So it may undermine the availability. What if we resolve the controller to synchronize the two parts, then it will incur less synchronization overhead due to slow control plane processing. So to fix the availability issue, we provide available cache eviction. Our insight is that we can associate additional in-switch metadata to the evicted record in the switch to ensure the availability. Well, here are the details. For the evicted record, controller will first mark the metadata, that is, mark the in-switch record as to be evicted such that the data plane can be aware of that the record is being admitted by the controller. Then controller will load the evicted record from switch to server for persistent storage before removing the record from the switch. But during this process, subsequent writes may arrive at the switch. So for each subsequent write on a to-be evicted record, FarReach will mark the in-switch record as outdated and forward the write to the server. So now server has the latest version. Well, for each subsequent read request on the evicted record, if the to-be evicted record is still latest, the switch can directly reply the read. But if the to-be evicted record has been marked as outdated, it means that some subsequent writes have already arrived at the server to update the server-side record. So FarReach will forward the read request to the server to get the latest version for availability. So that's how we fix the availability challenge by available cache eviction. But finally, we consider the reliability challenge and his problem. Under the write-back policy, cached records could be latest, but they have not been updated to the server. So after switch failures, all such in-switch latest records could be lost. So to avoid data loss, of course, we can make periodic snapshots on the in-switch cache. But as switch has very limited resources to store the snapshots, so we resolve the controller for snapshots. That is, controller will load the cache records from the switch. Well, during this process, as controller is slower, so subsequent writes could arrive at the switch and update some cached records. So if the controller loads the updated records or overwritten records, then it will finally get an inconsistent snapshot, which makes no sense for reliability. So to fix the reliability challenge, we propose crash-consistent snapshot generation. Our insight is that whenever FarReach receives a subsequent write, especially for the first subsequent write, it can send the original record to the controller. The original record refers to the version after the snapshot time point, yet before the first subsequent write. So controller can replace the overwritten record with the original record for crash consistency. So here are the details of our two-phase snapshot generation algorithm. Well, in the first phase, controller will trigger snapshot generation in switch. And in the second phase, controller will load all cache records from the switch. During the second phase, subsequent writes could arrive at the switch. So for for the first write of each cache record, FarReach will send the original record to the controller. After controller load all cached records, controller will notify the end of the snapshot period to the switch, and no more original record will be reported to the controller. So finally, controller can revert the snapshot to a consistent state based on the original records collected from the switch. So that's our snapshot generation algorithm. While the snapshot generation algorithm still exists a limitation. That is, it only avoids the data loss before the latest snapshot. But for the cached records updated or newly added after the latest snapshot, they are not protected, and such records could still be lost after switch failures. So to fix the limitation, we propose client-side record preservation. We borrow the idea of upstream backup and stream processing. In FarReach, clients will preserve the copies of cache records after the latest snapshot. So after each snapshot period, controller will notify clients to release the records which have been snapshotted by the latest snapshot. So to limit the client-side overhead. And after switch failures, we can use a recovery-based approach for zero-loss recovery. Well, for the server-side key-value stores, we can replace the writes of the latest records based on the latest snapshot, and the client-side preserve the records to update the servers. Well, for the switch, we can replace the cache omission decisions of the cache records based on the latest snapshot to recover the in-switch cache. So that's how we fix the reliability challenge by crash consistent snapshot generation with zero loss recovery. Here's our evaluation. For the server-side storage, we use server rotation to simulate tens of servers. Where for the in-switch cache, we compile our P4 program into the Tofino switch chipset. We use two baselines. One is no cache, that is traditional key value store without in-switch caching. And another one is net cache, state-of-the-art in-switch write-through cache. We conduct the following experiments. We use YCSB core workloads to evaluate the throughput, latency, and scalability. We also use YCSB benchmark to generate some synthetic workloads following the thin distribution to evaluate the impact of different parameters. Well, we also evaluate the performance of our snapshot generation algorithm and measure the crash recovery time. Finally, we compile all the methods into the same Tofino switch chipset to compare the hardware resource usage. But due to time limitation, I will only introduce 3 main experiments here. Well, the first experiment I will introduce is throughput analysis. Here we simulate 16 servers by server rotation and use different YCSB core workloads. Results show that FarReach can achieve larger throughput than baselines, especially for workload A, as workload A is skewed and write intensive. So the reason is that the in-switch write-back cache in FarReach can absorb the writes on cache records and reduce server-side load. Here's the second experiment about scalability. Here we use workload A, which is skewed and write intensive. We use server rotation to simulate different numbers of servers, ranging from 16 to 128. Results show that FarReach can achieve a throughput gain of up to 6.6 times the baselines under 128 simulated servers. The reason is that under a large number of simulated servers, baselines will suffer from serious imbalanced load. But for FarReach, as the in-switch write-back cache can absorb the frequent write, so it can balance the server-side load. Here's the last experiment I will introduce today. It's about the performance of snapshot generation. Here we use dynamic workload patterns such as the bandwidth includes both snapshot generation and cache management. We tune the snapshot periods. So the result shows that on the different snapshot periods, our snapshot generation has limited effect on the system throughput of FarReach. Well, here the result shows that FarReach will keep relatively limited control plane bandwidth usage. For example, under a small snapshot period of 2.5 seconds, the control plane bandwidth is around 1.4 megabytes per second, which is far smaller than the capacity of a network interface. So to conclude, we propose FarReach, a fast, available, and reliable in-switch write-back cache. We use the 3 design features to fix the 3 challenges respectively. We perform Tofino switch evaluation based on YCSB core workloads and the synthetic workloads. And here's the link of our source code. That's all for my presentation, and thank you for listening. I'd like to take your questions and comments. Thank you.